Studies Session 6, Frequency Distribution. Introduction. In trying to understand, interpret, predict, and modify behavior, psychologists engage in various forms of research that involve data collection. Such data represent observable behaviors that are recorded in numerical forms. This study session will expose you to how to summarize data into manageable forms using frequency distribution. Learning outcomes. When you have studied this session, you should be able to 1. Demonstrate how data can be put in a simple frequency distribution pattern. 2. Construct class intervals and enhance the use of tally marks with subsequent frequency values. 3. Determine exact limits and midpoint values in grouped frequency distributions. Regular frequency distribution. Oftentimes, when research works are conducted by economics, educationists, psychologists, political scientists, or sociologists, the dependent variable of interest is measured and represented with numerical numbers. Each participant's score on the dependent variable is thus recorded, leaving the research with a mass of unordered data for the whole research participants. These data are of little or no meaning until they have been organized and classified in a systematic way that will allow the introduction of statistical analysis like the average, standard deviation, and variance. Suppose that a training manager wants to evaluate how well his trainees have performed at the completion of a training exercise in accounting. He gave his trainees a test and their scores fall between 0 and 10. As you can observe, the data in Table 6.1 are unorganized and unordered and are therefore confusing and difficult to comprehend. In statistical terms, they are called raw or unclassified data. Items on raw data become more comprehensible when classified. The resulting table obtained after classifying raw data is called a frequency distribution. When the number of different scores in the raw data is not too large, the regular frequency distributions are an excellent way of summarizing a set of data. The scores in Table 1 range between 1 and 10, and it gives the number of different scores as 11. This is not too large, so regular frequency distribution can be used to summarize the raw data as shown in Table 6.2. Steps in constructing a regular frequency distribution tally. Number 1. List every raw score value in the first column of a table and denote this by the symbol X, with the highest score at the top and the lowest score at the bottom. Thus, 10 is at the top while 0 is at the bottom. 2. Run through the raw data either horizontally or vertically, recording each observed score against identical scores in the first column with a tally mark. Show the tally marks in the second column. After every 4 tallies, the 5th tally is used to cross the previous 4. It is a rule. It is aimed at easing the recording of frequencies. 3. When the tally is completed, the tally marks for each score in the first column are added up to find the frequency F and recorded in the third column. The frequency of each score shows the number of times a given score was obtained. You can easily read from Table 6.2 that 2 students had a score of 10, 5 students had a score of 9, 7 students score 8, and so on. Cross-check with table 6.1. 4. Add up the frequencies and place the total at the bottom of the frequency column. The Greek sign sigma means the sum of, and sigma f means the sum of frequencies. Is used to show this. It means the total number of scores in the sample. Sigma f and n must be equal. They are therefore used to check error in tallying. Thus, if sigma f and n are not equal, the tallying exercise should be repeated. Even when they are equal, it is still advisable to repeat the exercise to check for error of placing one or more tally marks wrongly. If the first tallying was done vertically, the second may be done horizontally to check for such error. You have learned that the frequency distribution is a convenient way to organize a set of data. You have also been exposed to the steps of constructing a frequency distribution table. You will now prepare a frequency distribution for the height of 24 students under this guided activity. The height in inches of 24 students are as follows: 66, 68, 65, 67, 64, 68, 64, 66, 64, 69, 69, 64, 67, 63, 63, 68, 67, 65, 69, 65, 67, 66, 69, and 67. To prepare a frequency distribution, step 1, make 3 columns. Step 2, list the height in order of size in the first column, the tally in the second column, and the frequency in the third column. Grouped frequency distribution. When data obtained in a research are relatively more, the regular frequency distribution might not be adequate in summarizing the data. Rather, the group frequency distribution becomes necessary. This calls for the grouping of raw data into class intervals, and the number of scores in each class interval is then recorded as frequency. An interval in which scores are grouped is called a class interval. Suppose a production manager is interested in the production efficiency of employees in his department. He selected 50 members of his department and recorded their performances in terms of number of cartons packed in 1 hour, as presented in table 6.3. Steps in constructing a grouped frequency distribution. 1. Calculate the range of the raw scores. This is obtained by subtracting the lowest value from the highest value. In table 6.3, the highest value is 75, while the lowest is 19. Therefore, the range 75 minus 19 gives us 56. 2. Determine the number of class intervals and the class interval size or class width of each interval. Points to note are: A. The number of class intervals must not be less than 10 or above 20. It is, however, better to have intervals between 10 and 15 for convenience. B. Certain interval sizes or widths are preferred. These are 2, 3, 5, or a multiple of 5 like 10, 15, 20, etc. C. All intervals should be the same size. This means that the range must be divided into a number of equal intervals. This formula could be used. Ci equals h minus L over I plus 1, or Ci equals range over I plus 1, where Ci is the class interval, H is the highest score, L lowest score, I class interval size chosen, and H minus L is the range. For the case under study, we have class interval equals 75 minus 19 over 5 plus 1. That will give us 56 over 5 plus 1, which is equal to 11.2 plus 1. Thus, the class interval is 12. Take this following tip. The higher the interval size chosen, the fewer the number of class interval. The lower the interval size chosen, the larger the number of class intervals that we emerge. Number 3. Arrange classes in a decreasing order of sequence with the lowest measure placed at the bottom of the table and the highest measure at the top, according to accepted rule. The first class interval from below is therefore 18 to 22. This covers the performance scores in unit packed of 18, 19, 20, 21, and 22, which makes the class interval of 5. The second interval of 23 to 27 covers the scores of 23, 24, 25, 26, and 27. The lowest score in each interval is called the lower limit, while the highest score in each interval is called the upper limit. Thus, 18, 23, 28, and so on are lower limits, while 22, 27, 32, and so on are respectively upper limits in the example in table 4. As guidelines, note the following. A. Ensure that the lowest score in the raw data is neither the lower limit nor the upper limit of the lowest class interval, or else the number of class intervals emerging may exceed or be less than the expected from your calculations. B. Classes must be mutually exclusive, that is, they must not overlap. This means that the upper limit of a class interval must not be the same as the lower limit of the next following interval. For instance, the interval 18 to 22, 22 to 26, 26 to 30 are overlapping class intervals. C. Classes must also be collectively exhaustive, that is, should cover all observations. To ensure this, the lower class interval should be able to accommodate the lowest raw score, while the topmost class interval should be able to accommodate the highest score. Thus, the class interval 18 to 22 accommodates 19, which is the lowest score, while 73 to 77 accommodates 75, which is the highest score in our example. D. Make the lowest score in each following interval a multiple of the interval size. Thus, we have 18, 23, 28, etc. with 5 as interval size. E. Gaps between classes must be avoided as much as possible. Number 4. Run through the raw data either horizontally or vertically and score each observation with a tally mark against its class until all observations are covered. 5. The tally marks in each class interval are added up to find the frequency for the interval. The frequency opposite a given class interval indicates the number of cases with scores in the interval. Thus, group frequency distributions lose information since the exact value of each score is not provided. Number 6. Add the frequencies and place the total at the bottom of the frequency column. 7. Always give your tables suitable headings. The exact limit and midpoint of class intervals. In group frequency distributions, class intervals do not show how values in continuous measurement forms should be presented. This is because class intervals make provisions only for discrete measures. This study session will show how to correct this anomaly using class intervals. Exact limit of class intervals are as well used in group frequency distribution. Within a class interval, a set of values are grouped together, thereby making it all scores in a class interval to lose identity. Within a class interval, a set of values are grouped together, thereby making it all scores in a class interval to lose identity. To represent all the scores in a class interval, therefore, the midpoint value is determined. Exact limits and midpoints. The limits, lower and upper, of the intervals in table 6.4 do not show exactly where each interval begins and ends. However, in statistical situation, it is very important to think in terms of exact limits. The interval 18 to 22 contains the scores 18, 19, 20, 21, and 22. A measure of 18, in essence, means anything from 17.5 and 18.5, which could be 17.5, 17.6, 17.7, up to 18.5. Thus, an interval of 18 to 22 has exact limits of 17.5 to 22.5. An interval of 23 to 27 has exact limit of 22.5 to 27.5. Exact limits are therefore established for each interval by subtracting 0.5 from the lower limit and adding 0.5 to the upper limit. These are then referred to as lower exact limits and upper exact limits respectively. This principle holds no matter the size of the interval. Exact limits are also called real limits. So, we can refer to the lower real limit and upper real limit of class intervals. It will easily be observed that each interval begins exactly where the one below it ends, which is as it should be. The interval with its exact limit should read 17.5 up to 22.5, which means it includes 22, 22.1, 22.2, 22.3, 22.4, but not 22.5. This is the interpretation, which is different from how it is read ordinarily. The midpoint of a class interval is the most central score in the interval. This is calculated easily by adding the lower and upper limits of each interval and dividing the sum by 2. The exact limit could as well be added and divided by 2. They give the same midpoint. The midpoint is represented by small letter x. Study session summary. In this study session, we have demonstrated how raw data can be presented in regular frequency distribution form. This involves the use of tally marks that are later converted and added up to find the frequency. You have also learned that the group frequency distribution is used when there are more than 15 values of scores. It calls for the grouping of raw data into class intervals, and the number of scores in each class interval is recorded as frequency. You also learned that exact limits are calculated by subtracting 0.5 from the lower limit to obtain the lower exact limit, and adding 0.5 to the upper limit to have an upper exact limit. The midpoint value is obtained by dividing the result of the summation of the lower and upper limits by 2. End of study session 6. Thank you for listening.